I don't think so. Ah, okay. Now it's moving. Okay, great. So the introduction is anyway done. So let's move forward. So I'll be talking about post-quantum cryptography here. So even though the workshop theme is AI in critical infrastructure, PQC or post-quantum cryptography is another topic which is very relevant to critical infrastructure. So we'll be talking about that. Okay. So I hope almost everybody here has heard of the term quantum computing at least, right? So yes, in general, somewhere in 1982, Richard Feynman, one of the I think by popularity after Einstein, I think Feynman would be one of the physicists who is so popular, right? So Feynman created a model that quantum mechanics could be used for computing and proposed one of the first ideas. It was not really a model, just an idea that quantum physics could be used for, quantum mechanics could be used for quantum computing. And since then there has been a lot of work. People have started developing various quantum algorithms. Even though there was no computer, they could use these principles of quantum mechanics and try to write algorithms, which in future someday if somebody could make a quantum computer, this algorithm could be implemented on that, right? So initially it was just a matter of interest for physicists. Somewhere in 90s, computer scientists started looking into it, mathematicians started looking into it. Still it was much of a theoretical subject, nothing physical. And then somewhere late 90s and early 2000s, people were able to build, various organizations were able to build like 1-bit quantum computing machine or something. Okay. Still not much interest from industry, but somewhere in 94, a mathematician, Peter Shor, he devised an algorithm which showed that if you had a quantum computer, you could factor integers very fast. Okay. So factoring problem is basically I give you 2 integers, I ask you to multiply it, easy. I give you an integer and I ask you find the factors of this integer. If you are lucky, sometimes it might be easy, but if I had chosen the integer by a certain method, it will be very difficult. At least currently, we don't know of any feasible algorithms, okay, even on the fastest computers, even on supercomputers. So when Peter Shor showed this, then there was an interest from mainly from governments, okay, mainly from spy agencies. Why? Because a lot of algorithms for encryption, etc., they are based on this factoring problem. And if somebody can factor really fast, they can also break the encryption used by other people. And that's why there was a lot of interest from the governments all around the world. They invested a lot, and still industry was not so much interested. Okay? So late 90s, early 2000s, not much of an industry interest. Okay? But since then, let's come to this. Okay? Since then, it has been observed that not just quantum computing, but in general quantum mechanics could be useful for various applications. Okay? So there are 3 main streams right now when we talk about quantum technologies on which a lot of work is happening. One is quantum computing, one is quantum communication, and the third is quantum sensing. Quantum sensing was shown to is actually seen to be by industry to be one of the most feasible and topics. Quantum sensors can be built and deployed in next 2 to 5 years. Okay? So a lot of investment is happening. Bosch itself is investing billions of dollars on that topic. Okay? And then quantum communication. One thing is, if you could establish quantum communication, a lot of communication security will be automatically solved. Okay. There will be a lot of other problems to be taken care of, but communication security part of it, that will be solved. Okay. So quantum communication is huge, and then quantum computing has taken up pace in last decade, mainly because it was shown that quantum computers, they can do a lot of simulation related problems. They could attack those problems really efficiently. Okay. Anywhere you need to do optimization, any kind of decision making that you need to do, where you need to traverse a tree a lot, okay, those kind of topics could be done using a quantum computer very fast. Okay. So that means a lot of application in various industries, whether it be wherever you need any sort of optimization, any sort of search. Okay. So whether it be AI and machine learning, lots of applications. Okay. Nowadays that's the big thing. Traffic optimization, financial optimization. So banks are interested, trading companies are interested. Okay. Climate modeling, of course, pharmaceuticals, okay, making new drugs. Okay. All those would be become much better. Okay. So of course, over here we are not going to talk about those. Over here what we are going to talk about is post quantum cryptography. Okay. All other topics here, to do this you need quantum mechanics. Okay. Post quantum cryptography, this is does not require quantum physics, does not require quantum mechanics. This is basically math or usual your computer science or even engineering, if you may call it. Okay. And we will talk about this. Okay. So what is post quantum cryptography? Well, it's a study of, if you just look up definition on, I think, Wikipedia or wherever, study of crypto systems that run on classical computers or current computers, but secure against quantum computers. So if an attacker had an access to a quantum computer, they'll still not be able to break these crypto systems. So there are many PQC techniques available, and some of them are as old as public key cryptography itself. Okay. So there are crypto algorithms based on coding theory. So there are crypto systems based on hash functions. There are crypto systems based on lattices, which we use in mathematics, and then multivariate equation based or isogeny based. These are, so if you know elliptic curves, something to do with elliptic curves. Okay. And since then, a lot of standardization process has been going on, and a lot of algorithms have been standardized by various agencies. Okay. So the most fashionable one or popular ones are based on lattices. Okay. The Kyber and dilithium, they are the two standards. Sphinx Plus is another standard that is based on hash functions. It's a signature algorithm. More signature algorithms, more encryption algorithms are on the way. Okay. So why PQC? Again, the conventional crypto systems, they are generally based on factoring algorithms, or they are based on what we call discrete logarithm problem. Okay. So if you hear of RSA based on factoring, if you hear of elliptic curve cryptography based on discrete log. Okay. And both these problems, they are in many aspects, they are kind of equivalent. If you know how to factor, you will be able to find discrete logs. If you know how to find discrete logs, factoring will become easy. So that Shor's algorithm could be used to crack any of those. Okay. So what will happen is, if a quantum computer became available, then our current methods of providing confidentiality or privacy or integrity and authenticity, they will collapse. Okay. So some of you might have heard of this term called harvest now, decrypt later. Quantum computer is not there today. It will be there sometime in future. So why should I worry now? Well, somebody who might be recording my communication today, they may not be able to decrypt it today, but in future, when they have access to a quantum computer, they will be able to decrypt it. Right? Or similarly, many times for authentication, we do digital signatures, etc. Those are verified, and those are verified using the public keys. Okay? And these digital certificates will be valid in future, right? So if I create a signature today, this will need to be verified against my digital certificate today. Right? So let's say NITK issues you your degree certificate. So and if it's a digital signature on that, this signature you will verify using the public key certificate of NITK. Okay? That public key certificate will be there in future also. Your degree certificate will need to be verified in future also. 10 years down the line, I could create fake certificates. Okay? That I graduated from NITK in 2025 or something. Okay? So not today, but 10 years down the line, there could be problems. Okay? So again, this has also turned into a huge business proposition, quantum communication, post-quantum crypto, a lot of investment going on, a lot of startups coming up. Okay? Our own country, they have this national quantum mission where they are investing like huge amount of money, and that's again over there post-quantum crypto becomes relevant. Okay? So of course, depending on who you talk to, they will tell you that quantum computer may not be there at all. It's not there now, it won't be there in 10 years, it won't be there in 50 years. Okay? So many people say that this is just a bubble. Okay? But they said so about AI. In 1960s, when people who were doing research in AI, and when they would get together for conferences, other computer scientists will throw stones at them. It has happened really. Okay? They will throw eggs on them, etc. So because AI guys were considered to be maniacs. They are considered to be lunatics. Okay? But today the situation is different. Okay? Even if you look at AI itself, 5 years ago, people thought AI is just a bubble, not much happening, just lots of hirings are happening. But then ChatGPT happened, and boom. Similarly, cryptographers were using blockchains since 90s, and nobody cared about blockchains. Okay? But 2009 Bitcoin happened, 2012 criminals started using Bitcoin, Silk Route happened, and then boom, everybody was working in blockchains. Okay? So this quantum bubble could be a bubble, but also it could be just it could be a debate, the way there is a debate about global warming. Many people will say global warming is a hoax, okay? Including the current president of United States. Right? They are saying that it's a hoax. Many people say moon landing never happened. So you have to choose who to trust. So but IBM, they way back in 2016, they put out a timeline that we are going to create quantum processors, and this timeline is from 2012. 2016 they had proposed this timeline, and up till 2024 they were actually pretty much on target. Okay? In 2024 they actually changed this timeline again, because now they are focusing on, instead of creating a lot of physical qubits, they are creating they are focusing on reducing the error correction now. So this timeline has been changed a little bit, but so number of qubits will be less, but actual logical work that will happen will still be on the timeline. Okay? So, and what does this timeline mean? Okay, I didn't explain qubits. Basically, you guys are computer science people, so you work with bits, right? Quantum computing work with qubits. Bits uses 0 and 1. Qubits, they are basically a qubit could have infinitely many values at any given point of time, but if you observe, it's always 0 or 1. Okay? You can think of qubit as a probability between 0 and 1, okay? But that's not correct. It's actually two complex numbers which satisfy certain properties, so it's much more than that. You can think of qubit as a direction on the sphere, okay? Three-dimensional sphere. Okay? So, and again, these are just for your visualization. Actual definitions are a little different. Okay? So, the information that is stored in a qubit, as long as you don't want to observe, could be anything. But when you observe, you get zeros and ones. And so the processing unit is qubit, like bit is in our computer science. And depending on how many qubits you have, you can do more and more computation. Again, how much memory do you have? How much execution time memory you have? How much storage you have? All those matter even in computer science, right? So, if you have a processor of 127 qubits, you can do certain amount of work. If you have a processor of 4000 units, you can do certain amount of work. Okay? In theory, if you had a processor of about 1300 qubits, okay, then you could break the elliptic of cryptography, which is even used today. And okay, this is, again, the keyword here is in theory. Okay? So, keep that in mind. So, and in theory, if you had a quantum computer of 4096 qubits, you could break the RSA that is being used today. Okay? Of course, these bits that I am mentioned here, they are what we call physical qubits. Okay? And these qubits that are mentioned here, they are what we call logical qubits. Okay? What is the difference? Physical qubits, they are actual quantum particles which you are using, but to do the computation which is equivalent to theoretical, let's say 2 qubits, you need actually many physical qubits, physical quantum particles. Okay? So, as of now, I think you need about about 1000 physical qubits to do work equivalent to 1 logical qubit. Right? So, that's where we are getting closer to. We have come a little below 1000 also at for different computations, but that's the rough thing. And this is because of so many errors that get introduced, so much signal noise, maintaining those quantum states, that is very hard. You are working with quantum particles, photon particles. Okay? So, you are talking about particles at the level of electrons and even smaller. Okay? So, controlling them is very hard. Okay? So, but if you listen to IBM, according to IBM, they say that by 2030, now they think that they will have quantum computers which can break the current RSA. Okay? And there was a survey done with a lot of quantum physicists, a lot of mathematicians, a lot of computer scientists and others who understand the technology. And this survey also shows that more than 50% of them believe that certainly by 2037, current RSA can be broken. Okay? So, 12 more years to go. So, your communication that you are doing today, and if you think you are secure, it will not be secure in 2037. Okay? So, for critical infrastructure, if they want to secure their products beyond 2037, then they need to think about post-quantum cryptography. Again, why? Because especially in critical infrastructure, the lifetime of the products is very long. My phone that I am using, I'll usually use for 2-3 years. Maybe after that my son will use for another year or so. Now possibly my son won't use it because he has grown up, but when he was a kid he was using that. Okay? So, our computers, our phones, they have a lifetime of about 3 to 5 years. Okay? Very few of us would be using a device more than 5 years. Okay? Let's say some of us are using maybe 10 years. Okay? But when you go to plants, there the machinery stays for 20, 30 years and maybe even more. Okay? So if there is a machine there now, and that machine will work continuously, it cannot be changed, you cannot easily update software in there or any firmware in there, and that machine will continue to work for next 30 years. And if you need some sort of public key crypto for security in those machines, by the end of its life, this crypto will be irrelevant. It won't be providing you any security. And when I talk about critical infrastructure, you could think of satellites also. Right? Satellites, you send a satellite to the moon or wherever, it's going to stay up there in space for many years. You send some machine to Pluto, it will keep going for so many years, right? And you want to communicate with it securely. Already governments are talking about space war, right? So, yeah. So why worry now? Again, well, even if you don't believe whether a quantum computer will come or not, okay, I work in industry, we have to work with compliances, we have to work with standards, and we have to follow those. Okay? If your product does not follow a certain compliance, you can't sell it. Okay? Compliances are coming up, whether it be United States, whether it be Europe, UK, Australia, New Zealand, Japan, China. Okay? All of them, they are bringing in compliances where if you are making a product, and if you want to sell the product beyond 2030 or certain date, okay, depends on which country you are talking about, you won't be allowed to sell those products beyond that date. So that's a loss. I am making a car today, and if I can't sell the car 5 years down the line, people won't buy this car. Because many times when we are buying a car, we are also thinking, what will be its resale value, right? So, and also then somebody says, hey, the date is 2030, I have to comply by that time. Why should I start worrying about today? I have 5 more years to go. The thing is, crypto is not easy to implement. It's not easy to deploy. It's very hard. Okay? Normally, if we see from 1980s onwards, okay, RSA came into picture in 1976, 77. Industry grade RSA was ready in early 1980, but actual deployment almost late 80s, early 90s. Okay. Elliptic curve cryptography was around since 1985. Only in 2000 onwards, commercial deployment. Okay. Even early 2000s, it was not so popular. The IoT ecosystem kind of they could not do without ECC. Even RSA, the same algorithm, just changing the parameter, just making the key lengths longer, that is not easy. Okay? It can take up to 5 to 10 years just changing the parameters. So if you have crypto that you want to implement, the time that you will need to deploy this solution, that can be anywhere from 5 to 10 years. Okay? And that, like, even though libraries are available, you cannot just take those libraries and put those on the product. The integration with your product, that takes time. Okay? So depending on what is your lifetime, how much do you need your information to be secure. Let's say if you need your information to be secure for 15 years, and your time to deploy a quantum safe solution, if that is even 5 or 10 years, you have to worry about when does the quantum computer will become a reality. If the quantum computer becomes a reality before your Y plus Z, then you are in trouble. You don't have security for that period. Okay? So that's why we need to invest right now. Okay? So then question is, do I really need security? Do I need post-quantum cryptography? Okay? It depends. For your daily, day-to-day transaction, maybe chats, etc., possibly not. Your casual chats with your friends, your simple you go online to your bank, do a transaction. If somebody gets to know 20 years down the line, and if you don't care about it, okay, So it all depends that what you are doing. You are buying something on Amazon today, whether you care about it or not, whether somebody gets to know what you purchased on Amazon or eBay or on some site. Right? But what if you are doing some transactions on a porn site? Maybe you may not want to other people to know that you are purchasing videos on a pornographic site. Right? What if I am having an affair outside my marriage today? 20 years down the line, even if I am on deathbed, my wife will kill me first if she gets to know. Right? So, what information we have and till when do we want to keep it secure? Okay? And that analysis needs to be done. In industry, in government, many times they take some grey decisions. Governments, they end up taking some very hard decisions. Right? And they need to protect that for almost forever. In United States, by law, they can protect certain information up to 60 years. Okay? They don't release that information. Okay? And 60 years later also they are releasing because lots of legal battles had there that government should be transparent, etc. So they said, okay, after 60 years we'll release. Okay? We still don't know what happened to Lal Bahadur Shastri in Tashkent. Right? So a lot of analysis needs to be done when in industry when you are working, or even in government when you are working, whether you need to, how long do you need to secure your information for. Okay? Similarly for authentication. Okay? Authentication is when we want to prove signatures, etc., when we want to know who we are talking to, when we want to know where did the data come from. Again, how long do you need your authentication credentials to be secure? Okay? So for your general online logins, most of the server based transactions, server side security can be upgraded faster. You don't have to worry about it today. Okay? On the other hand, if you are talking about some products in the field with long life, it could be your critical infrastructure, big satellites, it could be manufacturing plants. Okay? Then you have to worry about. There are different security controls, secure boot, secure update, secure communication. Then you have to worry about. Okay? Till when are you going to need these authentication credentials? Okay? So, yeah. So generally when we talk about products, generally when we talk about critical infrastructure, there are 4 main security controls that are relevant when we talk about security. So most of us, we have heard about secure communication, secure TLS. Okay? So that is one control. There are other controls. Okay? Secure boot. Okay? When a device starts up, we want to know if some changes were made to the device when it was offline. Many of you have parked your vehicles somewhere in the road, somewhere on the garage. Okay? An attacker, an adversary, an enemy, they come, get into the vehicle, get down the vehicle and make some changes. Okay? They access the vehicle, the diagnostic port is just behind the headlight. They take out the headlight, access the diagnostic port, make some changes to the vehicle and go away. How do you know when you start the vehicle if some changes have been made or not? In movies you have seen, right? Somebody comes and cuts the brake fluid, that thing, tube, etc., right? And then accidents happen. With vehicles where software is involved, at least with brake fluid, you see below the vehicle before getting into the vehicle, you will know something is wrong. Right? With electronics, etc., how do you know if some changes were made? Okay? So that's where secure boot comes into the picture. When your phone starts up, when you restart your phone, especially after some updates, etc., or your PC, generally a secure boot process takes place. Okay? Similarly, there is secure access. Somebody connects to your device, okay? Either online, either physically, using some port. Okay? How does the device know that this is an authorized entity who is connecting to me? So you take your car to the service center and they bring a device and they connect that thing to the car, and then they do some service to your car. They do diagnostics, etc. Okay? You take your phone to, let's say, a service center. They connect their device, and they MI guys know, MI phone will know that these are MI guys. Apple phones will know these are Apple guys, and so on, right? So that's the secure access. Okay? And then secure update. When you receive an update on your phone, I usually keep my phone here, so I'm again and again my hand reaches there to take out the phone. So yeah, so when you receive an update on your phone, how does your phone know that this update actually has come from either Google or Apple or whoever is your app provider is? Okay? Let's say your application, whatever application you are using. Okay? Because your phone is connected to the Wi-Fi, I am connected to the Wi-Fi, I could try to send some update to your phone. Okay? And nowadays, with devices, sending a malware disguised as an update is a very popular mechanism. Okay? So, a couple of years, or maybe now more than a couple of years ago, ASUS computers had this problem where they received updates disguised as updates from Microsoft. And if anybody installed that update, it was actually a malware. Okay? So how do you know the update has come from the right place? For all these three questions, secure boot, secure access, and secure update, you are wanting to know who is connecting to me, who is sending this data to me. And that's where authentication comes into the picture. Well, earlier this authentication used to be done using what we call MACs, okay? Message authentication codes. Nowadays, a lot of authentication is done using digital signatures. Okay? And all these three security controls, they get affected if a quantum computer is there. Okay? Similarly, secure communication involves secure authentication and involves encryption. Okay? And again there, quantum computer will be able to attack. Oh, actually, I already explained secure communication to you. Secure communication, I don't want to hope very likely you already know what happens in secure communication. Okay? So, usually when you want to set up a secure communication, when you go to, let's say, website, let's say www.nitk.com or .edu.ac.in. .ac.in. Yeah, .ac.in. Yeah. So when you go to this website, how do you know that you are really on NITK web page? Okay. Or more close to you, if you go to, let's say, www.hdfcbank.com. Right? How do you know that you are on that bank web page? Okay. So generally, your browser, when they connect to the server, okay, they don't know which server is this, because everything is happening online. You can't see who you are talking to, right? So they will say, hey server, hey hdfcbank.com server, I want to set up a secure communication with you. Can you prove you are hdfcbank.com? Okay. So generally, the server will send a digital certificate. See, this is my iCard. This is my digital certificate. So I am hdfcbank.com. So, but just because I show you I'm my iCard or a valid iCard, should you accept it? So what if I steal his iCard and show that, hey, this is a valid NITK iCard? Not good, right? So you should check whether I am the owner of the iCard. Okay? So the client, they will challenge that, okay, this is a valid certificate, this is a valid iCard, prove that you are the owner of the iCard. You are the owner of the certificate. And then they will provide some proof that yes, I am indeed the owner of the certificate. Okay? So that's the initial identification, authentication happens that okay, now the browser knows they are talking to hdfcbank.com. Okay? I am not going to describe full technical background of TLS here, but high level I am explaining. Okay? So this is part of the authentication step of the handshake. Before this authentication, there is negotiation, etc. So I am not telling you that. And after this, they will do what we call key exchange. Okay? And those keys will be used to secure the actual communication. So generally, if you are connecting to a HTTPS website, after this whole step happens, after the keys are exchanged and they verify that yes, these are the keys actually on the both sides, that's when your actual page will load, at least the sensitive information will load. After that, you will give in the username and password, etc. Okay? Yeah. So if you really want, I'll share the slides with you if you really want to go into like how at least we are providing quantum resilience, quantum security. So this is the whole workflow that we have. Maybe you can share the slides. Okay. So we did this. We have this from Bosch. We also have a paper on the topic. Some of the results are we did with various algorithms that are out there, post-quantum algorithms like Kyber for key exchange, Dilithium, Falcon for signatures, or Sphinx for signature. And usually when you implement this, you can mix them up in your certificates. Okay? So we did a lot of mixing of this signature schemes, encryption schemes, to see what combination is efficient for which particular use case. Okay? So again, I'm not going to go into that table, but basically this benchmarking, what it tells us, that for various levels of security that you need for your use case, depending on your efficiency requirement, depending on your bandwidth requirement, depending on your latency requirements, okay, you can use various combinations of these signature schemes or encryption schemes and have at least for your use case, something good enough. Okay. What these results also show is that you cannot just take some online open source library and just slap it on your product. Your product will break down. Okay? So similarly, this is a scenario of secure access where you have a ECU, electronic control unit, or vehicle control unit, and some diagnostic tool is connected to the vehicle. Okay? And we want to authenticate who we are connecting to. Okay? So again, here something similar happens where the tester, they kind of connect to the ECU and they say, hey, I want to set up a communication with you, give me access. So same story, they'll say, okay, prove that you are the right guy, prove that you are authorized. Okay? So this guy will give the certificate, the ECU will verify the certificate, then they'll challenge that, okay, prove that you are owner of the certificate, and the tester, they will provide the proof that yes, I am the owner of the certificate, and then this will continue. Okay? So this is actually much simpler than secure communication. The process is much simpler, and in fact, this is one of the simplest use case when it comes to cryptography. Okay? So again, here we did, and here we found something very interesting. When you are working with really old hardware, okay? So generally when you talk about PQC, people will say, oh, PQC are new algorithms, they are more complicated algorithms. So if you implement them, they will be very slow or they will take up too much bandwidth. Okay? What we observed that if you have really old hardware, some of the PQC algorithms, they work almost 10 times better than the classical algorithms, the RSA or ECDSA. So we were able to establish a connection in about 65 to 70 milliseconds compared to RSA algorithms, which takes almost, compared to ECDSA, which takes almost 800 milliseconds. Okay? These are special use cases, but in the modern hardware, there will be HSMs, hardware accelerators for classical algorithms, which do much faster work. So then we are defeated by the hardware implementations. But then our belief is that if we could also implement this on the hardware, if we could create HSM, then they will be also quite fast. Okay? So that part now we are working on, and we are doing that. Okay? So similarly, secure boot, when it happens, usually sometimes with phones and your laptops, the hard drive size could be pretty huge. Right? Even the boot sector itself, the master boot record, it will be pretty huge. Okay? and if I want to check the integrity of the whole device in one go, your startup time will be quite a bit. Okay? So usually the boot happens in secure boot happens in sequences. Okay? You start with the most critical data at the beginning, and then a little less critical data, and then a little less critical data, and you keep opening up some applications. Okay? So on an OS level, if you want to think, let's say you start from the kernel level. Okay? So you first check the integrity of the boot record, and then you check the integrity of the, let's say, kernel, and then you go to the user space. Okay? So again, here we implemented combinations, mixes of various post-quantum algorithms at various stages, and did a benchmarking that at various levels, how you use various algorithms, what happens. Okay? And we did benchmarking. Right? And here also we have the similar result for as in TLS, that you shouldn't use the same signature for all purposes. Okay? If you should, because if you use the same signature for all purposes, you will definitely lose big time, at least on either on bandwidth or on latency. Okay? So depending on use case, depending on your like whether you are working with sensor nodes or whether you are working at server level, like how much capacity you have, you can change this. Okay? And now I don't want to take up more time. Same thing we have done for secure update with different algorithms, implement them, right? So this I should have hit, but okay, now that's there, let's talk about. Basically, this is now some of the services. So this is kind of an advertisement for our Bosch, what we do. So Bosch now provides these services to various industry players, whether it be government, whether it be defense, okay? Critical infrastructure, where we provide them PQC training, migration related training, because most of the times the people in industry, they are not going to do their own crypto, but they should know which crypto to use, okay? How to integrate it securely, okay? When to integrate, in which use cases, okay? So which products you need this crypto, okay? You don't need to replace PQC everywhere, okay? In fact, if you do that, very likely your product will die. If you change all RSA by PQC, very likely you can forget about that product, it will die. So we work with various organizations and figure out where they need to replace with PQC. Okay? And when we are doing that, we have different solutions that we provide to them, like figuring out crypto inventory and figuring out which crypto needs to be updated. We have a simple solution, a software-based solution, where you already have your security infrastructure. It's just that you don't have the quantum resiliency, okay? And you don't want to change everything. So we have a very simple overlay solution, which we recommend. It's only temporary for most of the purposes, but if you need a temporary fix before you go to the real one, we have an overlay solution. And except for the initial setup latency, the cost is almost zero. So this solution works at zero overhead during your actual communication. Okay? And then, of course, our QR Shield is where we go to the core. We actually replace your full crypto. Okay? Instead of just doing a band-aid kind of a job, this is where we are working with you, and optimized implementation we do, secure integration we do. Okay? So again, I think I can skip this. This is again an advertisement for our offering, so let's do this. So this benchmarking that we are doing, just to again our setup, we have done this for various platforms. Okay? So the usual x86 and then various microcontrollers. So on ARM, on STM controllers, on other controllers. Okay? So and for various algorithms that are out there, some of them are already NIST standards. Some of them are going to become NIST standards, hopefully. Okay? So we work with this, okay? And the way we are implementing it is in a hybrid manner, because for many applications your hardware may be old hardware, especially it holds true in critical infrastructure where you have legacy hardware there, and if you want to implement crypto it can become very difficult. So we try to, you may not have crypto engines available, so we try to use whatever you have and implement this. Okay. So we have also now implementing at the hardware level. We have on FPGA right now we are testing out various algorithms, and we are doing optimized implementation of many hash based algorithms and many lattice based algorithms. Okay. And at least in some cases we have seen improvement up to 10 times faster. Okay. Yeah, there is some pictures of our setup that we have. Okay. And I don't think this was the last slide, but yeah, maybe this is the last slide. Okay, great. So usually there is one more slide, maybe I have hidden that. Okay. Yeah, so that's what we are doing in post-quantum crypto. I didn't want to go into the technical details, but if you have some questions, I would definitely want to answer those. Yes?
Sir, is there any relation between these supercomputers and quantum?
Relation? Not really. Okay. Supercomputers, they are still classical computers. You just stack tons and tons of CPUs, GPUs together in very efficient manner, and that's what you're doing basically. In a very, it's a very naive way of explaining. But here in quantum computers, you are working with quantum particles. You are working with quantum mechanics. Okay? So yeah.
No, then it is actually hardware or software?
Quantum computing is hardware. Post-quantum crypto is software. So, but if you are talking about quantum computing, whether it be quantum communication, again, you are sending various quantum particles, generally photons, but it could be other particles. You are just sending them from one place to another, okay, and you are doing communication based on those. Quantum sensing, again, you are using quantum mechanics, you are using quantum particles and trying to figure something out, like maybe some, if you have a pacemaker which uses quantum sensor, they are doing that. Or if you are mining equipment, trying to figure out what's 100 kilometers below the ground, if you are using a quantum sensor, they are working with based on quantum mechanics. Or whether it be quantum computers, again, various quantum particles. Again, I'll just use the term photon, the light particle, but it could be different, and you are trying to work with them. You are trying to control them in a way so that they, it should go to the first slide, I should have stayed there.
Sir, how to imagine that, how it will affect, the quantum computing hardware, how it affects, industry, how it affects the, communication channels, those kind of things I could not able to imagine.
Yes, and that's the part. Okay. First thing, very hard to imagine this qubit. There is information there, basically any point on the sphere could be stored there. Okay. But when you observe it, you always get 0 or 1. Heisenberg principle in your 10th or maybe plus 2, you might have heard that you can only accurately measure either the velocity or the position of a particle, right?
The wave of particle.
Of the particle, right? Either the velocity or the position.
Wave, sir. Because light has the dual property, wave and particle.
Yeah.
So either you can pass the wave or particle.
Or you can take it like that. Okay. So basically what is happening is, as soon as you observe, you are throwing some light, you are moving it, but also somehow its quantum states, they collapse and it becomes 0 or 1. And you might have heard about Schrodinger's cat. Schrodinger's experiment, you put a cat in a black box with a vial of cyanide, and you rotate you shake the box very hard, and at any given point when the box is shaking, whether the cat is alive or dead, you don't know, right? But when you open, you know for sure it's either alive or dead. The answer is 0 or 1. So that's the idea. When you observe, your answer will always be 0 or 1, but in between it could be any point on the sphere, okay? Or you can think of the probability, okay, to make your life easier. Okay? And again, as our colleague mentioned, when you are working with particles, they behave as particles, they behave as waves, and then there is a concept of entanglement, where two particles which are otherwise they are entangled, and a priori they are behaving kind of independently, but if you observe one, whatever state it may collapse, the other one will always collapse immediately to the other state. So if this one collapses to -1, the other will, okay, here we will talk 0 and 1. So if one collapses to 0, the other will collapse to 1, okay, and the other way around. Okay. So that's the concept of entanglement, and of course, in fact, even Einstein had difficulty believing this property, and only recently it has been proved. And in earlier days, Einstein did not even believe in quantum mechanics, and he is one of the arguably one of the best or greatest physicists alive, right? So if Einstein did not understand, we are mere mortals, okay? So don't feel bad about that. So I also don't understand, I just believe. Right? So, but what does this mean, entanglement? Now again, Einstein said something that has what is with greatest speed? Which thing has the highest speed?
Light.
Light. Some 30,000 meters per second or something, right?
Yeah.
Or 30,000 kilometer per hour, one of the units.
3 lakh.
Yeah, some 3 is there, I have also forgotten, right? But here, these two particles, they could be diametrically other ends of the universe. If you observe one, you immediately get the information about the other one. So this information that has traveled way faster than light, instantaneously. So Einstein's philosophy or his theory goes away, because Einstein says nothing can travel faster than light. Here you got the information immediately. So this thing, and they are not connected, it's not like they are algorithmically connected. So it's, of course I could program, write a program where, well, you know, value of one variable, the other variable will be always opposite. It's not like that, okay? A priori they are kind of relatively random. Only on observation they become same, okay? So this property again helps in a lot of calculation. And again, this interference, something in physics we studied about resonance, right? Waves, and there was this example on a bridge. Soldiers battalion won't walk in unison, but they'll walk randomly so that the bridge does not collapse. There are YouTube videos where bridges have started shaking. I don't know if there, I think one of the videos also shows a bridge being collapsing because people were walking in unison on that, right? So if two waves are in the same phase, they add up to create a wave which has much higher amplitude, but if their phases mix up, then they are destructive, right? So this is the part that is used for addition and subtraction, and then of course if you know how to add, you can multiply, and then you can divide, and then almost if you studied about Fourier series, etc., any function you can represent as a polynomial, okay, as close as you want, they will be very much, right? So this is what is used, this property is used, this property is used, and many more quantum physics properties are used. We are not going to go into those. So, but yeah, because of this, some properties which are very difficult to even measure, okay? And now when you are making them work like this, when you are trying to control them, you have to control them in a way so that you don't end up observing any of them. Because as soon as you collapse, no more calculation possible, okay? And that is very hard. So yes, it's very difficult to do, and that's why we don't have like large scale quantum computers. We very likely won't have quantum computers in our pocket, at least in our lifetimes, okay? But looks like quantum computers are going to be here in next 10 to 15 years. There will be some interesting quantum computers around. Yeah.
Sir, in this field, who all are the leaders, company-wise? You know, who all are into this?
D-Wave was one of the first companies that made a mark. They created devices. Okay? Since D-Wave, even the big ones, IBM is one of the bigger ones. Microsoft, ID Quantic, and many others are there. But IBM, Microsoft, D-Wave, they would be the big ones, I'll say. Yeah.
Thank you, sir.
Yeah. Yes. Yeah.
What do you mean when you say this quantum sensor?
Okay. When you say sensor, give me an example of a sensor.
Yeah, they sense the data like.
Sense the data.
Yeah.
So a sensor could be somehow it's figuring out the temperature.
Yes.
So when we used to use those mercury thermometers, right? You put the thermometer, the heat transfer happens, mercury expands, and now you can figure out the temperature, right? So here the same thing with quantum particles. If heat increases, the energy transfer increases, and if you can observe this quantum particle, the fluctuation will be much more accurate if you could observe it. Okay? In their mercury, when it's getting heated up, there are a lot of noise factors involved. Okay, and a lot of atoms within the mercury, they have to, their distance, etc., they will increase, etc., they'll speed up. Here you are measuring at the subatomic level.
Yeah.
Right? So
Okay.
that's
Sir,
all.
one more thing. Just my understanding about qubit after I see that diagram is like it is some value stored at any position on the sphere. Is it what?
You can think of it like that, yes.
Yeah. Okay, sir. Thank
So
you.
basically, these particles, they are always spinning,
Yes.
and they are spinning in all possible directions, like the Earth's rotation.
Yeah, yeah. Got it.
Okay? So
Angular directions.
is kind of, you can think of that spin as a qubit. Okay?
Okay.
Little more
But
thing has to be
when you
satisfied,
say spin again, finding a position will be difficult, right, sir? Like.
and that's why as soon as you observe it, it collapses either up or down. So +1 or -1. So in physics we use +1 and -1. In computers we treat the -1 as 0.
0. Okay.
That's it.
Okay, sir.
Yeah.
Quantum laser clocks, there are
Hmm?
laser clocks,
Laser clocks.
they are going to, in future, that is will be used.
Yeah, so laser-based clocks, again, a lot of work is happening. I really don't know where are they. That part I really don't know. But again, because quantum sensors are becoming so popular, but quantum laser clocks have been around even earlier, right? They have been there. Like I think I saw in CERN, in the CERN museum, there is one.
In America, they started using quantum laser clocks.
They could be. I saw it in the CERN when I had visited Geneva at some point. So yeah. But they have been there.
Navigation will be highly used. PNT architecture, it will be highly used.
Yes, all the sensors, I think, for navigation, barometer, thermometer, figuring out radar kind of topics. Okay? So we are throwing the laser and it comes back to us, right? So a couple of weeks back, I was in the satellite, I forget, SIS, some conference was there. Okay? And there, so many satellite companies, startups, they are doing quantum enabled radars. So yeah, a lot of work happening.
Sir,
Yes.
sir, actually you said that even in the present days, if we are having 4096 qubits
Yeah.
computing computer,
Yeah.
we can break our existing cryptographies.
Yeah.
What
RSA.
exactly is your meanings? It
Acha.
is decryption of the encryption, or from description of the hash key to the original text.
Just a second. Okay. Something has happened. Yeah. There is some just data if you are looking at, like, basically actual companies doing real life POCs. So it's not all theoretical. So this I skipped at that time, but let's come back to this. So generally when we are saying public key cryptography, and this This is relevant mainly as of now mainly for public key crypto systems, okay, asymmetric crypto systems. Okay. So if you are using crypto system whose security is based on mathematical problems like factoring or discrete log problem. Okay. So some of you might have heard Diffie-Hellman key exchange algorithm. Okay. So that or RSA encryption or RSA signature. Okay. So if you can factor, then if you know the RSA public key, that is public key, so everybody knows, right? From the public key, you can figure out what is the secret key. And if I can figure out the secret key, now I can decrypt or I can sign. Okay? So if I was doing Diffie-Hellman key exchange, in Diffie-Hellman key exchange, some g to the power a is sent, g to the power a modulo some prime p. Okay? So now g to the power, and this a is supposed to be the secret part. G everybody knows, and p everybody knows, and g to the power a modulo p everybody knows. From that, if I know how to calculate this a, and then I have broken the secret. Okay? So that will be possible. So
Actually, there are two parts. One is hashing part, another one is encryption part. So even both the conversion is possible.
So quantum computers, at least as of now, they cannot break the hashing. They cannot break the current hash functions. Okay? At least we don't know if of algorithms. Okay? So the encryption part, the signature part, that will be broken. But if I can break the encryption, then for example, the RSA, the hash is not really that complicated. Okay? So the hash, some sort of a hashing happens in RSA, but that is for integrity check. That is not for security part. Okay? So that can be broken.
Thank you, sir.
Yeah.
Sir, what do you mean by quantum algorithms? How to use them on digital computers?
That's the point. When we are saying quantum algorithms, generally you cannot implement them on our classical computers. Currently what we do is, we do sort of a simulation. Okay, and simulation means I am writing a program that will create some randomness and use that randomness to kind of have this sense of qubit. But everything is done as a simulation, and they are not really able to actually do the job. Right?
But there will be limitations, sir.
Of course, when you do simulation, then it's all the limitation of the classical computing will be there.
Yes.
Okay? But the simulation can give you some sort of convincing. Yes, sure, the quantum algorithm will work actual work. How much similar the fighter pilots, they do the simulations on ground. When you get in the air, the life is very different. So.
IBM Qiskit does that. All the universities produce several PhDs in quantum through IBM Qiskit.
Yeah.
Is it acceptable? Some journals will accept, some journals don't accept.
So when you are using Qiskit, Qiskit is also mostly a simulation. Okay? Though it is working with, on other side, with some quantum computing, but the Qiskit itself is a simulation. Okay? So it's trying to take multiple, let's say, quantum results and try to give you a larger result, which is just a simulated result. It may not hold true in real life. Okay? So, but Qiskit is again an acceptable simulation for many purposes. So, and especially if you are now working with Qiskit 2, it has much better error improvement, etc. Yeah. Yes.
What is the programming language you use for the quantum computing, sir?
Gates.
So there are many languages available, but to start with, if you know a little bit of Python, that's good enough.
Okay, so basically we can use Python for quantum computing. Suppose if we get some
So
computers in
there are
future.
already libraries available. So you write in Python. At the back end, some other algorithm is being used. Okay? So, but to start with, like if you want to use Qiskit, a little bit of Python, if you know. In fact, for Qiskit, if you know some programming language, you can work with Qiskit.
Okay, sir.
Yeah. So, and yeah. So if you know C or Java also, you will be good enough to start. Yeah. Yes. Any other questions? No? Right. Yeah. Are there any questions online? Uh, let's see. I don't see anything in the chat though.
So if there is no question, then I want to present a token of thanks to sir.
Hey.
So this represents Mangalore culture.
Oh, thank you. Thank you. Oh, one more. Thank you.
And I request everybody please come forward, we take group photo and then break for lunch.
Yeah, and if you want to reach out to me, you can just email me here. Okay? Or find me on. Even though my research topic is privacy, I am myself a very open guy. So you'll find me everywhere on.
What is the concept of university?
So the Bosch Cybersecurity University. So this is a program within Bosch. So I head this program, and this program is for creating various cybersecurity competency development programs. So this involves Academia Connect, this involves University Connect. So we are doing a postgraduate diploma in automotive security with BITS. We designed it, BITS plan is delivering it. Now we are working with some vendors like Coursera, etc., where we are designing the course and it will be delivered on Coursera. So Simply Learn, we did some projects with them. So we do this programs for various companies. I was telling him we are now working with IIT Chennai, that there we will be again delivering some programs. So various cybersecurity related programs. So yeah. So, yeah.
That's a nice one actually.
Hmm?
Very, very good. Very nice, interesting.